Okay, now I want to talk about chemical equilibrium. So the idea of dynamic equilibrium means that two things are going in the same rate, so forwards and backwards, and then that if you look away from it, it looks like both things are going in at the same time. So it looks like nothing is happening, although within the system that you're looking at, actually a lot of things are going on back and forth, but the overall change doesn't change. So given here the example of traffic, if you look at it both ways, you can see it's sort of like the forward reaction rate equals the reverse reaction rate. And of course, this is if the traffic is flowing, it's the same amount, but this is the idea. So think of it as sort of sameness and consistency. I think of it personally as balance. So if you've ever had a concussion before, one of the things they say is loss of equilibrium, loss of balance. So then it becomes harder to stand up. So, and there are many things that are not in equilibrium. Think, oh, equilibrium must exist everywhere. No, not really. If you have a cup of hot water, it's not in equilibrium. The temperature of the water is going down. So, but eventually the cup of hot water will go and will tune to be the same temperature of the surroundings. And that is when the water is at equilibrium in terms of temperature with the surroundings. So we also move towards equilibrium. So life is not in equilibrium, although we do have a term called homeostasis that describes the equilibrium that we have as a living thing. But our body temperature, except for rare circumstances, is not the same temperature as the surroundings. And we maintain that, and we also are in control of that, at least our bodies are, in regards to this disequilibrium, this non-equilibrium. So there are other things, though. So many other physical and chemical processes, like a cup of hot water, is not in equilibrium, but it's also not alive. But the water will slowly come to equilibrium with its environment. So, but for living things, though, they control this. We control this, and that's part of it. We respond to stimuli as one of the basic things when it comes to life. And so you could say, for us, life is having this uncontrolled, this controlled disequilibrium with your environment. So, and then of course, when the living creature is no longer is alive, then this disequilibrium vanishes. So before we talk about equilibrium more in depth, let's talk about the idea of the rate of chemical reaction. Some chemical reactions happen very quickly, sometimes they happen very slowly, and they also, under some circumstances they happen quickly, some circumstances they happen very slowly. Equilibrium, though, is when the forward reaction rate equals the reverse reaction rate. Not all chemical reactions are reversible. Many are, and but many are not as well. So the rate is like the speed. It's the change in concentration of the change in time. So it's a change of how many reactants we lose versus how much product we gain, and over time. So by that, if you are studying calculus, that's a derivative, right? So it's the derivative of the concentration. So also some common things. If it's a fast reaction rate, the reaction proceeds forward very quickly. In the slow reaction rate, it proceeds more slowly. The change of concentrations happen more slowly over time. And we can also control them. And so for us, we can control them and see what influences them. So why do chemical reactions happen? Well, among other things, they happen through collisions. So they have to be close enough, and when atoms and or molecules approach each other, what happens is they slow down because it is negatively charged, and we have to overcome this negative charge between them, and we'll talk about this later, it's called activation energy. So if they overcome the activation energy, and then if the collision happens, it's the right type of collision, then the reaction can turn to form products. But if there's not enough energy, they just bounce off each other and they don't react. So not every single collision is going to result in a chemical reaction. So for gas phase, there's lots of gas particles bumping around. There is a wide range of energies, and if there are enough energy in the gas particles to overcome the barrier, like I said, usually when things are flying around, when two gas particles or any particles approach each other, they slow down because their kinetic energy is turned into potential energy because of the electrostatic repulsion of their electron cloud. And this is true for every single case. And sometimes, well, they don't even have to touch. They can just approach each other, and then they can kind of sling like a spring being let go. They fly away. So if there's enough energy, then maybe it can proceed to products. Generally speaking, low energy collisions don't have enough energy to react. So I already mentioned here the activation energy. So not only overcoming the electrostatic repulsion, it also can break chemical bonds. So there are various things. Also, the orientation of the molecules is important. So it's not just, there's many things here that we're leaving unanswered. So, but as far as determining the reaction rate, the most important factors are concentration, and that's the amount of reactants and or products per volume, more reactants for the force going forward, and then the temperature. So this is a general rule. It's not a rule set in stone, but about every 10 degrees Celsius, you double the reaction rate. That's generally speaking how it works, but that's not entirely true for all circumstances. It's just true for many circumstances in general. But concentration and temperature are important. And if you think of this in terms of the collision model, right, so concentration means more stuff means more collisions, temperature means higher speed, and higher speed means more collisions. Also, it means more collisions that have enough energy to overcome the activation energy. So this makes sense. So, and the subject that we deal with this is called chemical kinetics. So this is how reaction rates move forward. So, and so there's a whole branch of study in chemistry. So to show you here is a reaction. It's only going one way in this case. So hydrogen plus iodine form hydrogen iodides. So hydrogen plus iodine make two hydrogen iodides. And you start off on the left. You have the low initial rate, and then if you increase the concentration, there's a higher rate, and then the very high concentration. That means that the rates just increase because there's going to be more collisions between the hydrogen and the iodine. Of course, collisions between the hydrogen and the iodine and the iodine, they don't really matter because they're not going to, well, even if they exchange atoms, you're not forming new compounds. Whereas the hydrogen and the iodine, when they react, they can form a new compound. So, aforementioned, increased temperature means faster particles, which means high energy rate. And this is mostly true. There's actually a point where if you increase the temperature, the reaction rate goes down. But this is more of an exotic thing. Like if you in the end, the particles are so energetic that they just kind of fly apart. So believe it or not, there is a maximum point where temperature doesn't matter. But generally speaking, we don't really reach that limit. But there actually is a range for temperatures for things to work. So here's the same idea and you can see here in these images, A, you have a little bit of a shadow, B, you have a medium shadow, C, you have a big shadow, which means that the particles are zooming around. Zooming around means more collisions, more effective collisions, because there's high enough energy to overcome the activation energy, and thus higher rate. So here are the ideas, though. Reaction rates increased with higher concentration, also generally increase with increasing temperature. And they, generally speaking, the reaction rates decrease as the reaction proceeds because the reactants become consumed. Unless you're adding more reactants in there, then because of course if the reactants are consumed, that means that the concentration of the reactants is going down, which means a slower chemical reaction. So, but what about dynamic chemical equilibrium? Well, some reactions go both ways. Many reactions only go one way. Many reactions go both ways, and we call the reactions that go both ways, they call them reversible. So they can move forward and they can move backwards. And when the forward rate equals the reverse rate, we call this dynamic equilibrium. It's not that it's not static, which means it it's not unchanging. It's just dynamic because if you look at the overall concentration, doesn't change. But they're still moving around, they're still reacting, but this is the forward rate equals the reverse rate. And it looks like the reactants products concentrations don't change. And so they are being consumed at the same rate that they're being formed. So to give you an idea here, for the reversible hydrogen plus iodine to make 2 hydrogen iodides, so you start off initially at all hydrogen, all iodine, no hydrogen iodides, and then as the reaction proceeds, you then get to a point where even though it's a dynamic equilibrium, they're still forming and also breaking back down. The reaction rate forward equals reaction rate reverse, but since it's not changing, this is a dynamic equilibrium. So this is a system then at equilibrium. So to give you an analogy of population, so let's say you have Narnia and Middle-earth for those people that like fantasy books. If there's not a lot of people in Middle-earth, people start moving towards it, and then eventually get to a point where the number of people moving out of Middle-earth is the same as the number of people moving in. Then this is like the population has reached a dynamic equilibrium. People are still moving, but the total net stays about the same. So then let's talk about the equilibrium constant, and we give it the capital K with the subscript EQ. And since the concentration of the reactants and products don't change, we can then put them into a constant that shows this is unchanging. And this is only one process. These are at equilibrium, so a chemical reaction at equilibrium. If they're not at equilibrium, this doesn't work. But if we get enough time, things will go and set a certain amount, and then this equilibrium constant forms. And it's true if it's at equilibrium, it's true for all circumstances. So if you look at this generalized equation, little a of reactant A plus little b of reactant C is an equilibrium with little c of product C and little d of product D. And then the smaller lowercase letters are the stoichiometric coefficients, and the capital letters are each of the coefficients. And this is how you describe the equilibrium constant. Then you take products on the top over reactants, and those brackets there, that bracket means concentration and concentration in moles per liter. And then you raise it to the stoichiometric ratios there for the powers. And then this formula, so the products raised to their coefficients multiplied together, but divided by the reactants raised to their coefficients multiplied together, these two terms form the equilibrium constant. And equilibrium constants are constant for each temperature. So if you change the temperature, you change equilibrium constant. So let's look at this reaction here. You have 2 N2O5s in equilibrium with 4 NO2s and oxygen. So the products are in the numerator and the reactants are in the denominator. For the denominator, there's 2 of the N2O5s, so it's a concentration of N2O5 squared. 4 NO2s, that means concentration of NO2 raised to the 4th power, and oxygen is raised to the 1st power because 1 is implied. So let's talk about the size of the different equilibrium constants. You can have very large equilibrium constants, like here the formation of hydrogen bromide from hydrogen and bromine. And you can also have a very small equilibrium constant, like the formation of nitrogen monoxide in the presence of nitrogen and oxygen. You can see that's a very small, so 10 to the minus 31, that's a very, very small number. And that's also, look at the temperature at 25 degrees Celsius. So if you change the temperature, in looking at this, for instance, in the bottom one, there's not an appreciable amount of nitrogen monoxide in the air that forms naturally at standard temperature. So let's talk about this with the hydrogen bromide. That's a large number. So products over reactants, that's a large number. So if you fractions, so think back to fractions. If you have a large number over a really, really tiny number, then then the whole number there becomes a very large number. And when we say this, we say that there are more products. We'll say it shifts towards the right being the products and the left being reactants. So this is a right-leaning chemical reaction. There's an equilibrium, but we tend to be heavier on the product side. Now look at the opposite here for nitrogen monoxide. So this one leans left, which means it tends to lean towards the reactants with fewer products. So it's a small KEQ is a small number. So you have the concentration of products squared over the concentration of the reactants. And there's a small number, which means that the numerator is a small number and the denominator is a big number, relatively speaking. So that means we have a little bit of products over a lot of reactants. So we have this reaction does not progress forward very much, and it stays most on the left. And this makes sense too as well, right? Because we live in a nitrogen and oxygen atmosphere for the most part, and we don't really get appreciable amounts of nitrogen monoxide in here. And that's a good thing because it's a very noxious gas. So generally speaking, if the equilibrium constant is small, the reaction does not proceed far. We have very few products. If the reaction chemical equilibrium constant is very big, we favor the forward reaction. We tend to shift right towards the products. And if the equilibrium constant is about 1, then it's about halfway. So you have both species. I would even say for the middle part, KEQ, if it's from like 1,000 to 1,000th, then you really do have to worry about the concentration of the reactants and the products being there together. So it really depends on which system you're looking at and what you need to control when you do this. So what about solid or liquid? So if you think of this, what is concentration? Concentration means amount per volume. Right, so what's the concentration of liquid water? Liquid water, for instance, it's moles per liter, and there's 18 grams per mole. So if you take a kilogram is 1,000 is a liter of water. So you take 1,000 divided by 18, you get 55.6. So the concentration of liquid water is 55.6 molar. Does that change? And the answer is no. Liquid water always is going to have that concentration. Therefore, since it's a constant, the equilibrium constant will absorb that amount. So same thing with solids. Solids have the same amount per volume as liquids, and so you can keep them out of the equilibrium constant, and then then it turns out just the gases and the solutions are the only ones that really participate in the equilibrium constant. Everything else is constant. So the here for this chemical equation, the decomposition of calcium carbonate to form calcium oxide and carbon dioxide. This equilibrium constant is just the concentration of carbon dioxide. So it's a one thing right there. And because the solids concentrations don't change, you could say, okay, well I can go ahead and put them in there, but then you'd have to look up the values. And so we just say that the values are absorbed by the KEQ. So that way we don't have to keep on looking up values for various things. So let's look at this. We already spoke about this equation before. Hydrogen plus iodine makes 2 hydrogen iodides. And let's say the mixture at equilibrium at 445 degrees Celsius, we just have to know that the temperature doesn't matter, it's just that its equilibrium is at a constant temperature. Equilibrium values are for hydrogen, concentration is 0.11 molar, iodine is 0.11 molar, and hydrogen iodide is 0.78 molar. What is the value of the equilibrium constant? And so put in the numbers, so it's products over reactants raise their coefficient, so it's hydrogen iodide product squared over hydrogen plus iodine, and then we put in the numbers 0.78 squared over 0.11 squared, and we then get 50. You get 50 for the answer. Let's do another one. So in this COF2, 2 of them in equilibrium with carbon monoxide and carbon tetrafluoride. The equilibrium constant is 2 at 1,000 degrees Celsius. In an equilibrium mixture, the concentration of COF2 is 0.255 molar, and the concentration of CF4 is 0.118 molar. What is the equilibrium concentration of carbon dioxide? This is a case you have one equation, one unknown. So if you look at the KEQ there, so it's products over reactants raise their coefficients. So it's going to be the carbon dioxide product, carbon tetrafluoride product divided by the COF2 reactant squared. You can solve for carbon dioxide. So solving for carbon dioxide, we get the equation as written there. Now we plug in the numbers and then we solve and we get 1.1 molar. And notice this, that you're just doing the math and rearranging it and putting the numbers in. So one equation, one unknown. So let's talk about when equilibrium is disturbed, and this is known as Le Chatelier's principle. And I know I don't speak French, and I hope I'm saying this correctly. That's how I always learn, is Le Chatelier. And so the idea is, if a system's at equilibrium and you shift the equilibrium, the system will shift back to counteract that equilibrium change. So kind of like I told you, balancing is kind of like equilibrium. So if I'm balancing and someone comes up and pushes me, I have to push back in order to keep on standing upright. So that's the idea of the same system. If you do something to the system, if you add reactance, then the system is going to react forward to decrease the reactance to bring it back to equilibrium. If you add products, it's going to go in the reverse direction to counteract that. If you take products away, it's going to shift towards products to make more. So basically the system is going to change to have the system go back into equilibrium. And this is kind of like here, if you have the Narnia Middle Earth, if you throw a bunch of people into Middle Earth, you know what? More people are going to leave. And they're going to leave Middle Earth until the system gets back to equilibrium. So this is trying to counteract that change. And I mean, there's lots of experiments with this, right? So if you win the lottery and suddenly have hundreds of millions of dollars, you know, your spending habits are probably going to change. You're not going to be like, you know, it's time for me to cancel all my subscriptions and eat ramen noodles, right? You're like, nope, we're eating caviar and we're going on trips. Right, so you change your spending habits with a sudden influx of cash. So like, you know, your income versus your expenses tend to have a sort of equilibrium. So same thing with chemical reactions. So let's look at some of these cases. So we have this reaction equilibrium, N2O4 in equilibrium with two NO2s. So what are we going to do if we add NO2? NO2 is a product, which means we shift left towards the reactant. So we shift left and we go form more reactant. So the system has too much NO2, so what happens, it's going to destroy NO2 and shift to the left. So that's the idea of the Le Chatelier's principle. So here it shows the pictorial model of that by adding more NO2, you're going to shift the reaction back to form more N2O4. So what about the other way? What if you add more reactants? Well, now the reaction is going to shift right. So it's going to shift right to form more products. You look at it as removing the stress of adding more N2O4. So that's the disturbance. And here's the same picture of that. You add more N2O4, which means more are going to break apart. And then the system will go back to equilibrium, or it'll approach equilibrium. What about changing volume? So changing volume is the same thing as increasing the pressure, and then you can see the increase in the pressure. It's the system is going to go towards wherever one has the more moles of gas. So the system's going to want to decrease the pressure. So well, if you increase the pressure, the system's going to try and decrease the pressure, and that means it's going to shift towards the side that has fewer moles of gas. And you have to look at the equation to figure that out. So for this case, though, for nitrogen, for ammonia synthesis, nitrogen plus 3 hydrogens forming 2 ammonias, if you increase the pressure, you're going to shift towards the side that has fewer gas particles, so that's shifting right. So that's how the system will go and counter against this change. So what about if we decrease the pressure? So increasing the volume is the same thing as decreasing the pressure. You will shift towards the side that has more moles of gas, because it's kind of artificially increasing the pressure. And in this case, it's a shift left. So it really just depends on the system. So you have to pay attention. I can't give a general rule of it's going to shift right or shift left. You have to look at it and then look at, see what's changing, and then decide which way it's going to shift. So this is the summarization here. Decreasing the volume causes the reaction to shift towards the particles that have fewer moles of gas. And this is the same thing as increasing the pressure. Increasing the volume causes it to shift in the direction that has more moles of gas particles. And this is the same thing as decreasing the pressure. And if there's equal number of moles of gas, it doesn't matter. So here's an example of this. So hemoglobin, for instance, we have In our red blood cells, we have a protein called hemoglobin that has 4 heme groups, and each heme can carry an oxygen. And also, interesting thing with this that hemoglobin is more receptive to oxygen the more oxygenated it is. So we like to stay oxygenated. So this reaction, it just depends on which way it turns, because they depend on the concentration of oxygen. So as we throw the blood flows through our lungs, the concentration of oxygen is high in the blood, so we shift right and form more oxygenated hemoglobin. But the oxygen concentration is low in the muscles, so the oxygenated hemoglobin will pop off on oxygen, and then the oxygen will go into our muscles then to be burned. So an interesting adaptation is fetal hemoglobin. So that's the unborn child a fetal child. It has a slightly different equilibrium constant than the adult hemoglobin. It's a little stronger, and because of that, it actually it's easier then for the oxygen from the mother will flow from the hemoglobin of the mother then to the fetus. So this is an interesting effect here. So let's change topics and talk about exothermic and endothermic reactions. You can think, for exothermic reactions, think of heat as a product. And then endothermic reactions, you can think of heat as a reactant. So same thing with Le Chatelier's principle. So exothermic reaction, heat as a product. If you increase the temperature, you're increasing the products, you shift left towards the reactants. If for an exothermic reaction, you decrease the temperature, you will then shift right to form more products to increase the temperature. Now, one thing to note, though, is that when you change the temperature, you change the reaction rate. So that's one thing you have to remember. Oh, you also change the equilibrium constant. So that's something to remember with this. And opposite is true for endothermic reactions. So energy is a reactant. So increasing the heat means that there's more reactants, and you shift right towards the products. If you decrease the temperature, you shift left towards the reactants to counteract that change. So here's an example of the exothermic reaction. So think of it as adding heat is the same thing as adding a product, and then you have a shift left. And then what about taking heat away? So removing the heat here, remove a product. If you move a product, you shift right to form more products. So Le Chatelier's principle at work again. So what about for an endothermic reaction here? So if you increase heat, that means that you're adding a reactant, you shift right towards products. And then if you cool this reaction down, you remove reactants, and you shift left then towards the reactants. So it just depends on the side of the reaction for chemical equation and how the equilibrium will shift upon changing the temperature. So we can do this, and we can see, for instance, here a cooler temperature, and in the equilibrium process between N2O4 and NO2, you can, on the colder temperatures, you shift to the left where it's clear, and a warm temperature shift to the right. If you might recognize that color. That's one of the colors that you see in photochemical smog. So if you've been to a very polluted area like Los Angeles or Beijing or Mexico City, there tends to be this kind of haze around the cities, and that's actually this molecule here, NO2. Really, I don't like this stuff that much. So here's the general thing: the temperature change equilibrium. For exothermic chemical reactions, increasing temperature cause a shift to the left because it's a product, and so you add products, you shift to the left. If you decrease the temperature, you shift right because the system tries to generate more products. So endothermic is opposite. So endothermic energy is a reactant. So increasing temperature means more reactants, so you shift right, direction of the products. And decreasing temperature means then you shift left towards the reactants because the system is trying to generate more heat. So let's talk briefly then about solubility product constants. So it's the same thing as the chemical equilibrium constant, but we're looking at sparingly soluble salts in general, so salts that do not tend to dissolve that much. So, but for a very, very large KSP, it means that it's very soluble. For a small KSP, and this is where we usually do the problems with this, it means that the solid not breaking apart is favored. And so salts dissolving, this is also a chemical equilibrium process. It means that the compound's not very soluble for a small KSP. So looking at this, for instance, so calcium fluoride or fluorite, it breaks apart into calcium ions plus, or a single calcium ion plus 2 fluoride anions. And calcium fluoride, that is a solid, is not included in equilibrium constant because the concentration of solid doesn't change. But the concentration of the calcium ion and the fluoride anion can change. So we just say the solubility product constant, the KSP, is the concentration of calcium ions times the concentration of fluoride anions. And the fluoride anions are squared because there's a 2 in front of them. So here are the KSPs for various things here. Copper sulfide, that's really small. It's a very, very small number. And lead sulfide, also a very small number. See, the sulfides do not like to dissolve as much. So let's do some calculations using the solubility product constant. What is the molar solubility of barium sulfate? So barium sulfate breaks apart into barium plus 2 and sulfate anions. And the KSP then is barium concentration times concentration of sulfate. But if we divide the molar solubility as the same, that means that the molar solubility is the amount of barium sulfate that will dissolve per mole. So if you put in a mole of barium sulfate, how much is going to dissolve? And we can call this S. So barium and sulfate, they're going to be the same amount, so it's just S squared. And if the KSP is equal to an S squared, that means the molar solubility is just the square root of the KSP. So it's very easy, and you show you the proof there. So plug in the square root of 1.07 times 10 to the minus 10, and then you square root it, and you get 1.03 times 10 to the minus 5 molar. So that means the molar solubility of barium sulfate is 1.03 times 10 to the minus 5 moles per liter, which means it doesn't really dissociate that much. And I have had the unfortunate ability that I have had to drink barium sulfate. They use it as a contrasting agent for X-rays and CT scans, and this stuff tastes terrible. I don't like the way it tastes. So let's talk about activation energy. We talk about activation energy, and equilibrium constant will say how far a chemical reaction to go, but it doesn't say how fast. So that's one thing. With equilibrium, it's all tied into thermodynamics, and the energetics are all tied in, but it won't tell you how fast the reaction will go. So, for instance, if you know the De Beers commercial, "The diamonds are forever," diamonds are not forever. So diamonds at this temperature and pressure will revert back into graphite. But it's going to take a very long time. It's going to take millions of years, of course. That is longer than history. History is all about 5,000 years. So because of that, a diamond might as well be forever. So you could argue with De Beers. I'm a chemist, though, and I can tell you diamonds are not forever. But looking at the energetics and equilibrium will not tell you how fast it's going to go. Only the reaction rate can tell you. And part of it is it deals with the activation energy, and that's the energy barrier that they have to overcome. So think of the activation energy kind of like, you ever trying to convince yourself to start writing a paper? You try and bribe yourself with dopamine and treats like, okay, after you start writing, you can then look at a cat video online, or you can eat a candy bar, so then suddenly you have to really, really convince yourself to start going. That's the activation energy. So chemicals have activation energy too. They need that energy to overcome an activation barrier to react. So there are some chemical reactions that proceed without activation energies, but generally speaking, you need to have activation energy. And the reason for this is because most chemical reactions come apart by collision, and since electron clouds are negatively charged, you have to overcome the electrostatic repulsion between electron clouds. So you also need to break bonds, and this requires energy. So there are certain ways you can go through, and but once there's enough energy to do this, to get over the energy hump, the chemical reaction can then proceed very easily. Generally speaking, the higher the activation energy, the slower the reaction rate, because you need more energy to overcome it. So you need to have more energy, and the more effective collisions that have enough energy to overcome this activation barrier. And like an advanced topic also is that actually some can be too fast and have too much energy to react, but that's a rare case. But I'm telling you now just so you can think about it and get more for your buck here for this education. So here is an image that shows, if you look at this, you have energy on the y-axis and the reaction coordinate on the x-axis. Just say the reaction coordinate is typically a internuclear bond. In this case, it would probably be the distance between the two hydrogen atoms. And as the reaction progresses, you can form then the hydrogen and oxygen react, and then you have to overcome this initial activation energy where you break the bonds, but then has obviously a very exothermic reaction. You see here that the potential energy of the products is lower than potential energy of the reactants, which means this is an exothermic process. And hydrogen and burning an oxygen is a very exothermic process. So, but you have to overcome that over activation energy. So how do we make reactions faster or slower? So how do we considering we can get around this activation energy barrier? So if there's a high activation energy barrier, you're going to have a slower reaction rate. But is there a way that we can speed up the reaction without changing the temperature? And the answer is yes, we can add a catalyst. Well, we already mentioned how we control chemical reactions: increase the concentration, increase the temperature. But also you can use a catalyst. Catalysts provide alternative paths that can lower the activation energy. And so, for instance, here, if you have trying to roll the balls up a hill, to the hill being the potential energy, if you provide an alternate path, you can roll them around the hill, and then it's much easier for the reaction to go forward. So that's what the catalyst does, is it provides an alternate pathway. And it's just the activation energy is significantly lower, and then because of that, then the reaction rate will go down. But the one other thing with equilibrium and a catalyst, so a catalyst does not change the equilibrium. Equilibrium stays the same. It's just much easier for the reaction and much more quickly to happen more quickly, and it just gets the equilibrium faster. But it's not going to change the equilibrium. So an example of this is the destruction of upper atmospheric ozone. So think of it like this: ozone, that's O3 plus oxygen makes 2 oxygens, 2 diatomic oxygens. And we need this protective ozone layer because it helps absorb the UVB radiation. So, the ozone layer does not rapidly decompose in oxygen, although UVB plus oxygen does form ozone, so the ozone layer is also being generated. And one thing about chlorines, like from chlorofluorocarbons, you can form an alternate pathway where the chlorine can react with oxygen to form this, and then the chlorine is regenerated. So it doesn't change the equilibrium, but it changes how quickly the equilibrium occurs. So we are living creatures. We have lots of chemical reactions going on, and they have to happen quickly. Not only that, they're very site-specific. So we have a specific type of enzyme called enzymes. I'm sorry, it's a specific type of catalyst called enzymes, and they're big blobs of protein, and they orient molecules so that wherever there is a collision, it's a very effective collision. So they're very big molecules, and they wrap around things. I'll show you some pictures in a bit with sucrose. So, well, if you look at this here, so sucrose is a disaccharide. It has 2 sugars, glucose and fructose, and you need to be able to break it apart. But an enzyme can do this really quickly. It's very hard to do this, and of course, you're in the human body. You don't want to have you don't want the body to run off of something really hot like propane, right? So you want it to be able to run on something that's not super hot, but then something that has a very specific chemical reaction. That's what our enzymes do. And so our protein-based enzymes. And then what happens is that the molecule, in this case sucrose, will absorb in an active site on the enzyme, and then the active site can then, it depends on how the enzyme works. Here, then the enzyme can break the bond. It can just break the bond between these two, this two simple sugars to then pop off the fructose and the glucose. So here's the review. Equilibrium, I call it balance, but it means that if you look at something and it's not changing, it's at equilibrium. So chemical action rates is how quickly the reaction proceeds from reactants to products. And generally speaking, how you increase the reaction rate is increasing concentration, increasing temperature, or the addition of a catalyst. So catalyst can greatly increase the reaction rate. Dynamic equilibrium is when reversible reactions, not all reactions are reversible, but some reactions are reversible, then when the forward rate equals the reverse rate. And for aqueous and gaseous reactions, we can use a term called the equilibrium constant to look at the values at equilibrium. And this constant, it does not change for any given temperature. So also when you do the equilibrium constant, you do not include the values of the concentrations of the liquids and the solids because they don't change. They're just absorbed in a constant. And Le Chatelier's principle states that you shift, a system at equilibrium will shift to counteract whatever change you give it to. And so we've talked about that. We've talked about for aqueous solubility salts, the solubility product constant. This shows how far things in the manner in which things dissolve in ionic compounds. And then we talked about the importance of catalysts to overcome activation energy. Well, it lowers the barrier for it. Here are the learning objectives and also the legal